Um, Hello everyone, good evening. So here we shall solve some KCET previous year questions on the chapter electrostatic potential and capacitance. So here, so any doubts if you have, then please write that in the comments section. We shall obviously clarify them. And in any other chapter of physics, if you have more difficulty, then please mention the name of that chapter also in the comments section so that we can give more priority on it and solve more and more questions on that chapter. Uh, um, Also, some important homework questions will be uploaded in the Sapience Education application. Mm, So please install our Sapience Education application, whose link has been provided in the description. So here we shall start from the very first question. It is told that a spherical drop of capacitance 1 microfarad is broken into 8 drops of equal radius. Then the capacitance of each small drop is. So we know that capacitance C is given as Q by V. If Q is the charge on some object and V is the electric electrostatic potential of that object, then Q is the ratio of Q and V is called as the uh, capacitance C of that object. So here for for a spherical conductor having charge Q, its electrostatic potential at the surface is given as kq by r if r is the radius of that drop, where k is given as k is equal to 4 pi 1 by 4 pi epsilon naught. So it is q by 4 pi epsilon naught r. So therefore the uh, capacitance C for a spherical drop will be given as q by v, that is equal to 4 pi epsilon naught into r, where r is the radius of the drop. Now it is told that this one small drop is now broken into 8 equal drops. So each drop, the radius of each drop we have to find. Let's say it is r. And these 8 drops are having equal radiuses also. So therefore we can say the total volume of the drop should be the same. So the total volume will be 4 by 3 pi capital R cube of the large drop, and that is equal to 8 times the volume of each small drop. It is 4 by 3 pi R cube. 4 by 3 pi, 4 by 3 pi will cancel. Then we will get R equal to 2R. So small r equals to R by 2. Small r equals to R by 2. Now here it is given that the capacitance of the large drop, that is equal to 1 microfarad. So this 4 pi epsilon naught R is equal to 1 microfarad. Therefore, the capacitance of each small drop, let's call it C1. So that will be 4 pi epsilon naught into small r. So that is equal to 4 pi epsilon naught into r by 2. So this is 1 microfarad divided by 2, that is half microfarad. So option 3 is the correct answer. Then here it has been told that the told to find the effective capacitance in between A and B in the figure shown. So capacitance A, so the net capacitance across A and B we have to find. So here it is of forming a Wheatstone bridge actually. Since why here we can see that 3 by 4, that is equal to 6 by 8. So it is a Wheatstone bridge. Wheatstone bridge. So it means that if the points A and B are connected across some voltage source, so then no current will pass through this 2 microfarad capacitor. So simply we can just cancel it. So this circuit is simply just equivalent to 2 capacitors in series and followed by 2 another capacitors in series, and these two branches are connected in parallel. So this is A and B, and this capacitance is 3 microfarad, this is 6 microfarad, this is 4 microfarad, this is 8 microfarad. So now this is equivalent to the equivalent capacitance of 3 and 6 in series, that will be equal to 3 into 6 by 3 plus 6. So that is 3 6 18 by 9, that is 2 microfarad. So and the equivalent capacitance of 4 and 8, that will be 4 into 8 by 4 plus 8, that is 4 into 32 by 12. That is 4 3 is 12, 4 is 32. So that is 8 by 3. Now this capacitance is 2 microfarad and this is 8 by 3 microfarad. Then their equivalent capacitance, that will be, they are connected in parallel, that's why their equivalent capacitance, that will be equal to uh, 2 plus 8 by 3. Simply we have to add them. So that is 3 is 6, so 14 by 3 microfarad. So option 4 is the correct answer. Then it is told an uncharged sphere, an uncharged sphere of metal is placed inside a charged parallel plate capacitor. There is a charged parallel plate capacitor, a charged parallel plate capacitor, and an uncharged metal sphere means it is a conducting sphere. It is a conductor. Is placed within the parallel plate capacitor. The lines of force means we have to draw the electric field lines. We have to draw the electric field lines for this conductor. So it means we know that in a conductor, the electric field lines are always normal to the surface or perpendicular to the surface. So the rule is that the electric field lines are always perpendicular to the surface of a conductor. Perpendicular to the surface of a conductor. So it means it will be somewhat like this only. So it means option 3 is the correct answer. Since in option 3 only we are seeing that the electric field lines are normal to the surface of the conductor. And it will not bend all the field lines towards itself. It can't bend all the field lines towards itself. So option 4 is not correct. 4 metal conductors having different shapes, a sphere, cylindrical, pier, lightning conductor, are mounted on insulating stands and charged. The one which is best suited to retain the charges for a longer time is. So we know that in a sphere, the charges are uniformly distributed throughout the surface. The charges are uniformly distributed throughout the surface. And for non-spherical conductor, in some regions, the radius of curvature can be high, and in some regions, the radius of curvature can be less, and some, yeah, can be large. So when the radius of curvature is large, so then the capacitance is also large. And when the radius of curvature at any point is low, so then it means that if some edge is having sharp edges, um, in case of sharp pointed edges, the radius of curvature will be low. So for those regions, the capacitance will be also low. So when capacitance is low, it means that it can't retain charges for a longer time. So in a sphere, the charges are uniformly distributed throughout the surface, and the capacitance is also capacitance is also high. Capacitance is also high. And for non-spherical conductors, the radius of curvature is not same at every region. Radius of curvature is not same throughout its surface, throughout the surface. So it can't retain charges for a longer time. So, so I can say its capacitance will be also low. Capacitance will be lower than spherical conductors. Its capacitance will be lower than that of spherical conductors. So it means that a sphere will be more suited for retaining the charges for a longer time. So option 1 is the correct answer, the sphere. Then it is told that the potential to which a conductor is raised depends on the amount of charge or the geometry and size of the conductor. So here you know that Q equals to CV, and so V equals to Q by C. So the potential to which a conductor is raised, that will obviously depend on the charge, since V is proportional to Q, and the value of capacitance, it depends on the geometry and the size of the conductor. The value of the capacitance of any conductor will depend on the geometry, means the shape, geometry, or I can say shape and size of the conductor. Size of the conductor. So it means that the electrostatic potential V, that will depend on the charge also, that will be inversely proportional to the capacitance also. So the the correct answer is option 3, since it depends on both the amount of charge and on the geometry and size of the conductor. Then it is told that the work done in carrying a charge q once around a circle of radius r with charge q at the center. So as we know that the electrostatic force or the electric force, or I can say the electric field, is obviously a conservative field, or I can say the electric force is obviously a conservative force. Conservative force. It means that work done in a closed path will be zero. Work done in a closed path will be obviously zero only. Work done in a closed path will be zero. And here also we can see that when a charge q is placed at the center, and a small charge q is being moved in a circle of radius r, so then the electrostatic force of repulsion is acting radially outwards. It is acting away from the center, and the displacement is happening perpendicularly, means the displacement is happening tangentially along the tangent, and the force is radially outwards. So the angle in between the force and the small displacement dr, that is 90 degree. It will be f into dr into cos 90 degree. So that will be 0. So at every instant, the small amount of work done will be 0, which is dw, that will be 0. So the work done in in this closed path in carrying a charge q once around a circle, that will be 0 only. So the option 4 is the correct answer, which is none of these. The answer will be 0 work is done. Then here, an air-filled parallel plate condenser has a capacity of 2 picofarad. A parallel plate condenser means a parallel plate capacitor. Its capacitance is 2 picofarad. The separation of the plates is doubled. So if the separation of the plates is d, now d will change into 2d, and the interspace in between the plates is filled with wax. Interspace is filled with wax. So when it is not filled with wax, when air is filled, so then the capacitance is 2 picofarad. And when when wax is filled, if wax is filled here, and if the separation is 2d, then the new value of the capacitance will be equal to new value of the capacitance will be equal to so here C will be equal to obviously epsilon naught A by D if A is the surface area of the capacitor plates. If A is the surface area of the capacitor plates, and so A is the surface area, so then C dash will be equal to K into epsilon naught A by D, where K is the dielectric constant. No, it will be epsilon naught A by 2D. Okay. So therefore, C dash, we can see that will be K by 2 epsilon naught A by D. Now epsilon naught A by D value is 2 picofarad, and the new value of capacitance is increased to 6 picofarad. So therefore, we can see that the value of K by 2 into this will be 2 picofarad, that is equal to 6 picofarad. So 2 and 2 will cancel. So therefore, K is equal to 6. Therefore, the dielectric constant of the wax is 6. So option 4 is the correct answer. Then here it is told if a slab of insulating material 4 into 10 power minus 3 meters thick is introduced in between the plates. So it is the thickness of the slab. The thickness of the slab is equal to 4 into 10 power minus 3 meters. So it has been introduced in between the plates, of a parallel plate capacitor. The separation of the plates has to be increased by 3.5 into 10 power mm, minus 3 meter to restore the capacity to original value. So let's say the initial thickness was D. So now the new thickness is D plus D naught, suppose. Let's say D plus D1. So here the thickness has to be increased by 3.5 into 10 power minus 3 meter. The dielectric constant of the material will be. So here the thickness is T. The dielectric constant of the material will be. So initially, the initial value of the capacitance, that is C, that is equal to epsilon naught A by D. A is suppose the area of the plates, and D is the separation between the plates. And okay. And here initially air was there in between the plates. The new value of capacitance that will be equal to, so Here we can assume that it is equivalent to two capacitors connected in series. One value is C1, one value is C2. So this thickness will be T and this thickness will be D plus D1 minus T. D plus D1 minus T. Now, so when they are connected in series, so then it will be then it will be C1 C2 by C1 plus C2. Okay, so therefore the new capacitance will be C1, which is C dash. From here we can also say 1 by C dash. So the the capacitance should remain same, that is being told. So 1 by C dash will be equal to 1 by C. Since why C dash should be equal to C. Here this is given that the new value of capacitance should be equal to the previous value of the capacitance. So therefore this will 1 by C dash will be 1 by C1 plus 1 by C2, that should be equal to 1 by C. So therefore we can say that 1 by C1, so that will be D plus D1 minus T by epsilon naught A. Here air is there and here we have the slab. Here we have air. Here also we have air. Okay. So this will be epsilon naught A plus the dielectric constant has been asked. So K, so this will be T by epsilon naught K epsilon naught into A. T by K epsilon naught into A. And that should be equal to D by epsilon naught A. So here, from here we can see that D by epsilon naught A we can cancel. So epsilon naught A we can cancel it. And then we have D plus D1 minus T plus T by K, that is equal to D. So D and D also will get cancelled. So it means that D1 is the separation by which the plates has been increased. That is 3 point. D1 is, so this is T and this is D1, that is 3.5 into 10 power minus 3. So therefore 3.5 into 10 power minus 3 minus T, that is 4 to 10 power minus 3 plus 4 into 10 power minus 3 divided by K, that is equal to 0. So therefore 4 by K, 10 power minus 3 also I can take as common and then I can cancel it. 4 by K, that will be equal to 4 minus 3.5. So that is 4 by K, that is equal to 0.5. So it means K should be equal to 8. So K is equal to 8. So the dielectric constant of the material should be equal to 8. So therefore option B is the correct answer. Then here it has been told that 8 drops of mercury of equal radius, 8 drops of mercury of equal radius combine to form a bigger drop. The capacitance of a bigger drop as compared to each small drop is. So let's say the capacitance of each small drop is C and the capacitance of the larger drop is C1, suppose. So its radius will be capital R, and the radius of each small drop is say R. Here it is told 8 drops have equal radius. So now, therefore, the volume should be same. The volume of the the volume of the big drop, that should be equal to the sum of the volumes of all the 8 small drops. So it will be 8 into 4 by 3 pi r cube. That will be equal to 4 by 3 4 by 3 pi capital R cube. So 4 by 3 pi will cancel. So R is equal to okay, R is equal to 8 r cube whole power 1 by 3. So that is equal to 2 r. So R is equal to 2 r. Therefore, the capacitance C, that will be equal to Q by V. So it drops, okay. So C for the capacitance of a sphere, the capacitance of a conducting sphere, that will be equal to, so we know that V is equal to KQ by R if the charge on the sphere is Q, then the electrostatic potential of the conducting sphere will be V equal to KQ by R. So it means that Q by V, if we do, that will come 4 pi epsilon naught R. So this is the capacitance of a conducting sphere. So here the capacitance of each small drop will be 4 pi epsilon naught into R, and the C1, that is the capacitance of the big drop, that will be equal to 4 pi epsilon naught into capital R. Now capital R is equal to 2R, so that will be equal to 2 into 4 pi epsilon naught into small r. So it means that the capacitance of the bigger drop is 2 times of the capacitance of each smaller drop. So option A is the correct answer, that it is 2 times. The capacitance of the big drop is 2 times of that each of the small drop. Then here it has been told that an electrician requires a capacitance of 6 microfarad. He needs an equivalent capacitance of 6 microfarad in a circuit across a potential difference a, a potential difference V of 1.5 kilovolt. So it is 1500 volt. A large number of 2 microfarad capacitors which can withstand a potential difference of not more than 500 volts are available. The minimum number of capacitors required for this purposes. So here, to form 6 microfarad, we can connect actually three 2 microfarad capacitors in series. Since why? The the applied voltage is very high, which is the applied voltage is 1500 volt, 1500 volts. So since the capacitors of since the capacitance of each of these capacitors is same, so the voltage across each capacitor will be 500 volt. Each capacitor will be 500 volt, since it will be 1500 divided by 3, that is 500 volt. So now their equivalent capacitance here, that will be 2 by 3 microfarad. Since why? When when three capacitors are connected in series, C1, C2, and C3, so then here the equivalent capacitance will be given as um, the reciprocal of 1 by 1 by C1 plus 1 by C2 plus 1 by C3. So here, if the three capacitors are same, each of them are 2, then the C equivalent will come 1 by 2 plus 1 by 2 plus 1 by 2, or 1 by 2 into 3. So it is 1 by 3 by 2, so it is 2 by 3 microfarad. And each and so here we have to form 6 microfarad as the equivalent capacitance. So when we know that if two capacitance, if suppose three capacitors are connected in parallel, so then the equivalent capacitance is obviously given as the sum of them. So here also, if we connect these 2 microfarad capacitors, uh, suppose if we connect them parallel, in parallel we connect this group of 3 capacitors 9 times. 9 times if we connect these groups of 3 capacitors in parallel, so then the equivalent capacitance here in this case will come as 2 by 3 into 9, which will give me 3 3 are 9, that is 2 3 are 6 microfarad. So it means capacitors are how many minimum number of capacitors are required to achieve uh, an equivalent capacitance of 6 microfarad. So here we have groups of 3 in each branch. We have groups of 3 capacitors, and there are 9 such branches. 9 branches. So therefore the total number of capacitors required, the total number of capacitors required, that will be equal to 3 into 9, which is 27. 27 capacitors are required. So option D is the correct answer. Then in figure, charge on the capacitor is plotted against the potential difference. Charge is against the potential difference. 120. Okay. So here the capacitance is obviously constant, since y the slope is constant. So the capacitance will be equal to q by v, which is equal to the slope of this graph. So which will be 120 microcoulomb divided by 10 volts. So it will be 12 microfarad. And then, and the energy stored, the potential energy stored in the capacitor, we know it is uh, qv by 2. Since y it will be equal to the area under this graph of q and v. So that will be equal to half into q, that is 120 microcoulomb into 10 volts. So that will be equal to 600 micro into coulomb into volt. So coulomb into volt is obviously joule, so it is microjoule. 600 microjoule. So 12 microfarad and 600 microjoule. So option B is the correct answer. Then here it is told the electric field and potential of an electric dipole. We have an electric dipole minus q plus q. Its separation is 2a. So here P is equal to q into 2a. As we know, it is the dipole moment. So along its axis, here R should be much more than a. So then if R is much more than a, then a point very far from the electric dipole, the electric field on the axis, that is given as 2 kp by r cube, 2 kp by r cube, where k is equal to 1 by 4 pi epsilon naught, and q p is equal to the dipole moment, that is q into 2a. So here, therefore, the electric field on the axis, that is inversely proportional to r cube, and the electric potential V at on the axis at some value r, which is much more than a, that will be given as k into p dot r, k p dot r by r cube, k p dot r by r cube. So p dot r, so we can also write it as p vector dot r cap divided by r square. Since by r vector, we can say that is equal to r magnitude of r, which is r into r cap. So therefore we can say the electric potential at any point on the axis that is inversely proportional to r square. So the answer will be option C, since y the electric field is proportional to 1 by r cube, and the electric potential V is proportional to 1 by r square. Then here it is told two tiny spheres carrying charges 1.8, two tiny spheres carrying charges 1.8 microcoulomb and 2.8 microcoulomb is Q1 and Q2. They are located uh, at a distance of 40 centimeter apart. Then the potential at the midpoint of the line joining the two charges. So at this point P, we have to find how much is the potential at point A. Suppose at point A, how much is the net electric potential at the point A? So that will be equal to the potential at A due to the charge Q1 plus the potential at the point A due to the charge Q2. So that will be equal to, uh, we know that it will be KQ by R. So it will be equal to KQ1 by R. Now R, it is the m- midpoints. So this length I have to take R, R that is equal to 20 centimeter. Okay, so it will be KQ1 by R plus KQ2 by R. Since potential is a scalar quantity, so we have to add them algebraically. So it will be K by R into Q1 plus Q2. So K is equal to 9 into 10 power 9. K is equal to 1 by 4 pi epsilon naught, which the value of this is 9 into 10 power 9, as we know. It is Newton meter square per Coulomb square. Uh, so divided by R. R is 20 centimeters, so it is 20 into 10 power minus 2 meter, 10 power minus 2 meter, and into Q1 plus Q2. So it is 1.8 plus 2.8, and this is in microcoulomb, so into 10 power minus 6 coulomb. So this will be equal to 9 by 20 into 1.8 plus 2.8, that is 4.6, into this will be 10 power 9 minus 6, that is 3, 3 plus 2, that is 5. This much volts. So this will be equal to 2 tens are 20, 2.3. So then this will be 0.9 into 2.3. 2.3 into 0.9 is how much? 3 nines are 27, 2 nines are 18, 20, so 2.07. So approximately we can tell 2.1 into 10 power 5 volts. So option D is the correct answer. Then here it is told a parallel plate capacitor is charged by connecting a 2-volt battery across it. A 2-volt battery is connected across it, and it has been charged to some charge Q1, let's say. So Q1 will be equal to C into V, C into V1, where V1 is equal to 2 volt. Now it is disconnected from the battery and a glass slab, then so this is the initial case. So it is the situation, initial situation, and the final situation is this. Final situation is the plates. A glass slab is being introduced. A glass slab is there, which is being introduced in between the plates. Glass slab is introduced in between the plates. Glass slab is introduced in between the plates. Glass slab. produced it between the plates. So here, so let's say the dielectric constant of this glass slab is K. So here, since it has been disconnected from the voltage source, so the net charge should be conserved. The net charge on the capacitor is conserved. The net charge will be conserved. It means the initial charge will be equal to the final charge. So the initial charge is C into V1, and that will be equal to the final charge, which is C dash into V final, let's say. So C dash will be obviously equal to K times C, since why the class slab of dielectric constant K is being introduced. So therefore, this will be C V1 is equal to Kc into V final. So therefore, V final will be equal to V1 by K. So it means what? So the dielectric constant will be obviously more than 1. So the V final, the final electrostatic potential, it means the potential difference across the capacitor plates, that is V final, that will be obviously less than V1. Here V1 is only the initial potential difference across the two capacitor plates. So the final electrostatic potential, that is less than the initial value of the electrostatic potential. So it means and the Q will remain same. So the initial energy stored, that will be equal to Q1 into Q initial into V initial by 2, and um, the final value of the energy stored, the initial value of the energy stored in the capacitor will be Q1 into Qi into Vi by 2, and the final energy stored will be Q final into V final by 2. Now Q final and V final, they are same, but V final is less than V initial. So obviously we can say that the final energy stored will be obviously less than the initial energy stored. It means the energy stored will also decrease, and the potential difference will also decrease, and the capacitance will increase. So therefore we can say, therefore here in this case, the capacitance increases and capacitance increases and the net charge on the capacitance, that remains same. It is not changing, and the value of the potential difference, that will decrease, and the energy stored in the capacitor, that will also decrease. So these two quantities will decrease. So it means option D is the correct answer. Then here it is told that a parallel plate capacitor with capacitance C1 with a dielectric slab in between its plates. There is a dielectric slab of dielectric constant K uh, between its plates, is connected to a battery. Is connected to a battery. It has a potential difference of V1 across its plates. So it means the net charge on this capacitor will be equal to C1 into V1. So it is the initial charge. And when the dielectric slab is removed, keeping the capacitor connected to the battery, the new capacitance and potential. So it is the initial situation. Initially, this will happen, and finally, afterwards, the dielectric slab is removed. So then the new capacitance is C2, and the voltage source is already kept connected. Then the potential difference across this capacitor, that is told, that is V2. So it means the final charge on this capacitor will be C2 into V2. Okay, so now since the battery is kept connected, so V1 will be equal to V2 only. And since the dielectric constant is removed, so then uh, here C2 will be obviously equal to C1 by K. Since by here C2 will be equal to epsilon naught A by D, and here C1 that will be equal to obviously K into epsilon naught A by D. If the area is if the surface area of the plates is A and D is the separation in between the plates. Okay. So therefore C1 is obviously K times C2. So it means that C2 is, and K is obviously more than 1 only. The dielectric constant value of any dielectric slab will be obviously more than 1. So C1 will be obviously more than C2, or means that C2 will be obviously less than C1. C1 is more than C, so C1 more than C2 and B1 equal to V2. So option B is the correct answer. Then here it has been told that 5 capacitors value of 1 uh, farad are connected as shown in the figure. The equivalent capacitance in between A and B is. So here also one Wheatstone bridge kind of thing has been formed. Here you can see that this is the capacitor 1 microfarad, here also 1 microfarad, and again here 1 microfarad. This is also 1 microfarad, and this is also 1 microfarad. So it is the equivalent circuit for this, we can say. So now, as you can see that 1 by 1, the ratio of these two equals to the ratio of these two 1 by 1. So it means that no current will flow across this 1 microfarad capacitors if this A points A and B are connected to some voltage source. So it means this can be written, this is equivalent to, this is, wait, okay. So this one is the point A, this one is 1 microfarad, and this one is 1 microfarad, and this one is 1 microfarad, this one is also 1 microfarad. So across points A and B, these two capacitors are connected. Then we can say that this is equivalent to, so two capacitors are connected in series, so their equivalent will be 1 by 2, and here also the equivalent will be 1 by 2. And since they are connected in parallel, so the equivalent capacitance will be half plus half, that is equal to 1 microfarad. So it means option D is the correct answer. Option D, which is 1 microfarad, is the correct answer. Then here it has been told that uniform electric field E exists along horizontal direction as shown. The electric potential at point A, here it is told that the electric potential means VA at the point A, it is VA. And so we have to, okay, a small point charge Q is small point charge Q is taken slowly from point A to B along the curved path as shown. The potential energy of the charge when it reaches at the point B is. So the potential energy of the charge at the point B, that is equal to Q into VB, means where VB is the electric potential at the point B. So VB will be equal to VA minus E into X. Since why? We know that in the direction of the electric field, the electric potential always decreases. So this rule we have to use. The rule is that in the direction of the electric field, the direction of the electric field, the electric potential always decreases. The electric potential always decreases. For this reason only, we have that the electric field is given as minus dV by dx, or so V will be equal to minus integral E dx. from x initial to x final, then we will get v, which is v final minus v initial. Okay, so it means that the work done uh, by okay, work done by the electric force, or it is the negative of the work done by the electric field on unit positive charge. So here the electric field is constant, so the potential difference VB minus VA, that will be equal to minus of integral E dx from A to B. So that will be equal to E is constant, so it will come outside of the integral, and then so XB minus XA, so that will be equal to X only. Here it is told that the distance in between B and A is X. So VA minus EX. So therefore, the the potential energy of the charge Q at the point B, the potential energy of the charge at the point B, it is Q into VB, which is VA minus EX. It will be Q into VA minus EX. So option C is the correct answer. So hope all of you have understood the solutions of all these um, questions based on the previous year KCET exam on the chapter electrostatic potential and capacitance. Still, any doubts if you have, then please write that in the comments. We shall obviously clarify them, and um, please install our Sapience education application also, where we shall upload some important questions based on the previous year KCET exam, which shall be obviously helpful for your exam. So thank you everyone